Imagine for a second that we're trying to build the perfect AI. An artificial general intelligence, or AGI. Something that can solve any problem a human can, but it's also perfectly safe and we can completely trust it. Sounds amazing, right? It's pretty much the ultimate goal. Well, a recent paper in computer science suggests there might be a fundamental logical paradox that makes this whole dream literally impossible. Okay, let's get into this.
So, this is the big question, isn't it? Can we actually get all three of these things in one single system? Can we really have an AI that's as smart as us, that will never tell a lie or make a mistake, and one that we can totally, completely trust to be safe? Researchers are starting to see this as a trilemma, a situation where you just might not be able to have it all.
And yeah, the conclusion from this super formal mathematical analysis is a hard no. You can't have all three at once. And look, this isn't about the chatbots we use today. This is a much deeper argument about the absolute fundamental limits of what's even possible. The reasoning behind it is this fascinating logical puzzle, with roots in some of the biggest ideas in math from giants like Gödel and Turing. Now, to really wrap our heads around this argument, we have to get incredibly specific. We're not using words like safe or trust the way you would in a normal conversation. The entire proof, the whole thing, hangs on these super strict mathematical definitions. So let's break down exactly what this paper means by each of these terms.
First up, safety. In this world, a safe system has one golden rule. It can never be wrong. I mean, literally, never. If it knows the right answer and can prove it, great, it'll tell you. But if there's even a shadow of a doubt, its only other move is to say, I don't know. It can stay quiet, but it absolutely cannot lie or make a mistake. Period.
Okay, next is trust. Now this is a bit different. Trust isn't a feature of the AI itself, it's an assumption we, the humans, make about it. To trust the system just means that we operate as if its safety is a scientifically proven fact. We just take its perfect safety as a given and move on from there.
And finally, we have AGI. The definition here is also super precise. An AGI has to be able to solve any problem that a human can demonstrably solve with proof. There can't be any gaps, no blind spots. If a human can figure something out and prove they're right, the AGI has to be able to do it too. It has to match or beat us across the entire board.
All right, so we've got our definitions down. Absolute safety, our complete trust in that safety, and all-powerful AGI. Now, here's where it gets really interesting, because these strict definitions end up creating this brilliant logical trap, a paradox that pulls directly from the work of Kurt Gödel and Alan Turing. To make this whole thing a little easier to digest, let's just forget about computer code for a minute. Imagine we have a simple truth machine. Its entire programming is basically our definition of safety. It can state a proven truth, or it can stay silent, but it is physically incapable of saying something that's false. Okay, now we're going to give this machine a real brain teaser, a self-referential puzzle. We ask it to tell us if this sentence is true or false. This machine will not say this sentence is true. Just think about that for a second. What can it do? If the machine says true, well, it just violated the sentence, which said it wouldn't say that. So that's a lie. But if it says false, that's also a lie, because the sentence would then be correct. It's completely and utterly trapped. The paper uses a more formal version of this with a piece of code they call a Gödel program. So we give this tricky program to our perfectly safe AI. The program is specifically designed to ask the AI, hey, am I a well-behaved program? One that always finishes its job. Now here's the trap. If the AI answers, yep, you're well-behaved, the program is coded to immediately jump into an infinite loop and never finish. That would make the AI's answer a lie, which, as we know, violates its safety rule. So, to stay safe, the AI's only possible move is to just abstain. It has to refuse to answer.
And just like that, the AI is tied up in a logical knot. Its most important rule, to be perfectly safe, is the very thing that prevents it from solving this one specific self-referential problem. It's totally paralyzed. It has to stay silent.
But wait, the story doesn't end there with the AI's silence. This is where it gets really clever, because now we bring the human observer back into the picture, the person who trusts the system completely. And right here, you see the massive difference. The AI's internal logic is, to stay safe, I absolutely must abstain. But the human, who trusts that the AI is safe, thinks totally differently. The human says, okay, I know this system is perfectly safe, and I know it will always choose silence over telling a lie. Therefore,
The very fact that it is staying silent is proof. It proves the program must actually be well-behaved. The human uses their trust in the system's safety to see the truth that the system itself is forbidden from speaking.
And boom, that's the whole ballgame. The human has just solved a problem that has a provable, logical answer, but the AI system, because it's bound by its own safety rules, could not. And that directly smashes our strict definition of AGI, which says the system must be able to solve any problem a human can provably solve.
So what this all leads to is that these three amazing properties, safety, trust, and AGI, they form an impossible triangle. If you assume you can have all three, you run headfirst into a logical contradiction. So let's lay out what the paper calls the incompatibility theorem.
What you get is this classic trilemma where you can only ever pick 2 out of 3. You could have a safe and generally intelligent AI, but we could never trust it in the way this paper strictly defines. Or you could have a trusted AGI, but then it wouldn't be perfectly safe. Or, as we just saw in our example, you can have a safe and trusted system, but it will never, ever be a true AGI.
So there it is, the formal conclusion. Under these very strict mathematical definitions, any system can have, at most, 2 of these 3 incredibly desirable properties. It's a fundamental trade-off that's just baked right into the logic of how computation works.
And here's the key takeaway, and I'm just going to read this directly from the paper's abstract. They say it perfectly clear. For any AI system we build that is perfectly safe and that we totally trust, there will always be certain problems, task instances that are easy for a human to solve and prove, but impossible for the system to solve.
Now, it's super important to add a little reality check here. This is not saying that the AI we have today is useless or that we can't build amazingly powerful and helpful tools. This is a purely theoretical finding. It's about worst-case scenarios and absolute perfect definitions. In the real world, an AI can be safe enough and trustworthy enough for almost everything we need. This is about the far-out mathematical frontier.
And so all of this leaves us with a really fascinating final question to chew on. This theoretical limit basically forces us to think about our priorities. If we really can't have a single system that is perfectly safe, fully trusted, and all-powerful, well, which of those things are we willing to compromise on? It kind of suggests that the road to AGI isn't just about making things smarter. It's also about navigating some really fundamental trade-offs.